Okay, guys, so this will be your introduction for the SR flip-flop lab. So we'll go over kind of how these circuits are able to store data. Basically, this whole lab is an introduction to memory and how data or bits are able to be stored. And then, so we'll go over how these are, in particular, these SR flip-flops are able to store data. So what we have drawn here so far is just one part of the SR flip-flop circuit. This is called the SR latch. Okay, so we have two NAND gates. So this symbol here is the symbol for a NAND gate. Okay, so we have two NAND gates. You can see that the output of one of the NAND gates goes to one of the inputs of the other, and vice versa. So we have this flip-flop of the outputs going to the inputs of the course other NAND gate, which is why we get this SR flip-flop. All right, that's where this flip-flop term comes from, is where we're flipping the outputs to the inputs of the other NAND gate. We have these inputs, S bar, which is the complement of S, and then R bar, which is the complement of R. We say S stands for set and R stands for reset. All right, and we'll see where these bars, why it's called the complement of S and the complement of R in a second when we get to the next part of the circuit. But for right now, all you need to know is that this S is the input of this. Is the top input of this NAND gate, and then this R is the bottom input of this NAND gate. Right, that's all that's really important at this point. And then we'll kind of talk about the truth table for this SR latch. Okay. Before we get into the truth table for this SR latch, these are NAND gates, so we need to kind of remember what the truth table for a NAND gate looks like. So for NAND gate, we have two inputs, input 1 and input 2. Should look familiar from last week. And then we have an output. All right, we can have 4 combinations of different inputs that we can input into this gate. And then the output of a NAND gate will look something like this. So we'll have the 1, 1, 1, 0. All right. And you can refer to your manual from last week if you don't remember exactly where this truth table comes from. But this truth table is important when we're talking about this SR latch because it involves NAND gates, right? So we'll need to remember this information. So if we're building out the truth table for this SR latch, our two inputs are going to be the complement of S and the complement of R. All right, so let's just go through this truth table, and as we go through it, it'll become apparent how this device is able to store information. And then the output will be Q, and then Q complement. All right, this complement just means it's going to be the opposite. So we'll see that Q and Q complement will always be the opposite of each other, the inverse of each other. So if Q is a 1, Q complement is a 0, and vice versa. Okay. So let's go ahead and say that our S is going to be 1, and then our R is 0. So at this input for S, we input a 1, and then for this input at R, we input a 0. All right, looking at this truth table, right, we can see that anytime an input has a 0 in it, we're going to output a 1. So it doesn't matter what the other input is, right? It doesn't matter what this input here is. If R is 0, then this output for this second NAND gate will be a 1. Okay, so for Q complement, we'll get an output of 1 over here. Okay, now if Q out is a 1, you can see that the output of Q complement is hooked up to the second input up here for this first NAND gate. And if we have a 1, 1 input for this NAND gate, Q, our output, if both of these inputs are 1, looking at this NAND gate truth table, you can see our output is 0. So Q will be 0. And so what I told you earlier about these two always being opposite, you can see that that's true in this case. Now let's go ahead and say that we change our input from 0, 1 now, or from 1, 0 now to 1, 1, and see what our output is. So instead of our R here being 0, we now change it to a 1. Okay. So we still have our outputs over here. So if this is a 1, and we have our Q Q before, right? This was 0 and 1. So our Q before this is now going to be a 0 because this output 0 is hooked up to this input. So if we change this R to a 1 and this is still 0 from this output, then the output of this 1, 0 is going to be still a 1, right? 1, 0, or sorry, 0, 1. We come here 0, 1 for a NAND gate has an output of 1. So our Q complement is going to be 1 there. All right, and if Q complement is 1 and our complement of S is 1, then we can see that Q is going to stay as a 0. All right, so pressing 1, 1 doesn't change our output in this case. It's still 0, 1. All right, so now let's change our input from 1, 1 to 0, 1. So let's get rid of this, all of these numbers here. And for S, we now have a 0, and for R, we now have a 1. Okay, so if, again, by the same reasoning that we had before, if S is 0 and if any input has a 0, you can see that the output will be a 1. Okay, so that since this S is 0 here, that means our output Q is going to be a 1. So we can put 1 for our Q. All right, and if Q is 1, that means this first input on this second NAND gate is going to be a 1. And since that's a 1 and our R is a 1, then that means our output Q complement is going to be a 0 because 1, 1 has an output of 0. So that's going to be 0 there. All right, so let's go ahead and now press 1, 1 again. So going from here to here, we might expect to get this same output here, right, of 0, 1. But let's just see what happens if we go from 0, 1 to 1, 1, right, and see what our output is going to be. All right, so we change S to 1. All right, we still have an output here, or we can still say that this complement of Q is still 0. Okay, since the complement of Q is 0, the input for this S NAND gate is going to be 0, which means that the output of this gate is going to be 1. So this is still a 1 over here. This Q is still 1. Output Q is still 1. And if output Q is still 1, that means we're still inputting a 1, 1 into this second NAND gate, which means our complement of Q is still going to be a 0. All right, so you can see now, just from this chart here, that if we go from 1, 0 to 1, 1, we have an output of 0, 1, okay, in both cases. But if we go from 0, 1 to 1, 1, we have an output of 1, 0 in both cases. So another way of writing this truth table, okay, is going to be, we can rewrite this truth table, S and R Q, sorry, that's just Q, this is Q complement. If S and R is 1, 0, then this is still going to be 0, 1. If S and R is 0, 1, then this is going to be 1, 0. And if S and R is 1, 1, we can just say that our output is going to be the memory. Or in other words, it's going to be whatever the previous input was, right? And you can see that in our truth table here, right? So our S and R of 1, 0 gave us an output of 0, 1. When we pressed 1, 1, we still have 0, 1. So it just keeps whatever our previous input was. And then if we change our input now to 0, 1, which means our output is 1, 0, right? And we press 1, 1, then that means that we're going to get back a 1, 0 still because our previous input was 1, 0. So whatever this previous one was, that's what our 1, 1 output would be, okay? So this is how the SR latch part of the SR flip-flop works, okay? Now you might be wondering what happens if I hit, if I just have 0, 0 for S and R, right? And if we have S and R, we get some contradictions, and it's not really an important case. So what we say is just this is an invalid entry. I don't want to spend too much time talking about this case, but basically it's not interesting to us, right? It doesn't give us an output that we're interested in. So we just say that it's invalid. Okay, it's not a case that we use in this SR flip-flop with NAND gates. Okay, so this is the output for just the SR latch part of the SR flip-flop. Now let's go ahead and draw the SR flip-flop in its entirety. So that includes 2 more NAND gates. So we have a NAND gate there. And these two have 2 outputs connected to each other. And then these 2 inputs are S and R. And then the central input that are connected to each other we call the clock. So we have our set, our reset, and then our clock. And then these 2 outputs for these 2 NAND gates now go to the input of our the 2 inputs of our SR latch. So we have this part stays the same from what we had before. All right, and then we have our outputs. The output here goes to the input there, and then the output here jumps over that and then goes to the input there. Okay, and so where this again is S complement and this again is R complement. All right, and then, oh yeah, this is Q, and then this is Q complement. So now let's make another truth table in the case of this full SR flip-flop circuit, okay, with our four different NAND gates. So we can rewrite our truth table similar to the way that we did here, but instead we're going to add this other term for the clock, right? It's another check that we have to do. So we have our S, our R. We'll put the clock at the front here, and then we'll have our outputs Q, and then Q complement. Okay, now let's see what we get here. So if our clock is set to 0, okay, if our clock is set to 0, and looking again at this NAND gate, if our clock is set to 0, that means our output is always going to be 1. Okay, so no matter what S and R are, no matter what S and R are set to be, if the clock is 0, then the output here is going to be 1 on both of them, right? If this is 0, which means that our output, if the output of S and R are both 1, then that means S complement is 1 and R complement is 1. And if we go back to this chart that we have here, that means if they're both set to 1, the output that we got was whatever the memory was, right? So our output here will be memory. And again, memory just means that it'll be whatever the previous state was. And it doesn't matter what we press for S and R. All right, so if the clock is set to 0, no matter what we press, no matter what input R and S and R take, this output for Q and Q complement will stay the same. Okay, it'll be whatever was already stored in the memory. Now if we do the case where the clock is now set to 1, and we have a 0, 1 input for S and R, so instead of clock being at 0, we now set that to 1, and then we set this to 0 and this to 1. Then the output of this first NAND gate, if this is 0 and 1, will be 1. So that will stay as 1. And then the output for this second NAND gate, if both inputs are 1, is going to be 0. So this becomes a 0 here. So because this output is 1 and this output is 0, you can see that this complement of S is 1, this complement of R is 0. And if we take that and look at this previous setting, or this previous truth table that we made for just this SR latch part, where S complement is 1 and S complement is 0, we can see that the output is 0, 1. So if our clock is 1 and S and R are set to 0, 1, our output for Q and Q complement are 0 and 1. Okay. Now let's do the case where our clock is set to 1 and our output now is 1 and 0. Or sorry, our input is 1 and 0. So we change our S from 0 to 1. We change our R from 1 to 0. That means the output of this first NAND gate is now a 0. and the output of this second NAND gate is now a 1, right? Because 1, 1 has an output of 0 from this truth table for NAND gates, and 1, 0 has an output of 1. So that's how we get these outputs. Now we have our S complement is 0 and our R complement is 1. If we come back to this chart here that we made earlier, an input of 0, 1 gives us a Q and Q complement of 1 and 0. All right. So you can see that basically what this clock does is it keeps, if the clock is off, it keeps our memory from being changed unless, no matter what we hit S and R for. Okay, but if the clock is on and then we set S and R to be a certain input, our output will mirror whatever our input was. Okay, so this is a way that we can prevent ourselves from accidentally pressing a button and changing what our stored memory was. So that's the purpose of the clock. If it's 0, then it doesn't matter what S and R are, we get whatever we had before. If clock is set to 1 and we have a new input, then our output will be whatever our input was. Okay, and then just as another example of this invalid case, if our clock is set to 1 and then we have 0, 0 here, right? So if our clock is set to 1 and then S and R are both equal to 0, that means both of our outputs over here will be both 1. Oh, sorry. If these are all 1s, sorry. This is the case that I want to do. If these are all 1s. So if those are all 1s, then 1, 1, 1, 1 for all of these, and for both of these NAND gates, then we get an output of 0 for both of these. Right. And if both of these outputs, if S complement is 0 and R complement is 0, then what we get is this invalid case. So we'll never have the clock on and be pressing both of these at the same time, basically. It's not a case that we care for. It doesn't achieve anything that we're looking to do. Okay. And the final case, right, is if clock is set to 1 and then both of these are 0. In this case, if both of these are 0, the output over here, right, the output is 1 and 1. And if the output is 1 and 1 for S complement and R complement, then we get the case where we have memory, right? So we get this case over here. So this is memory. So if all we do is press the clock and don't press anything for the S and the R input, then we'll still only have whatever we had in the memory stored in the memory. Okay, so this is how flip-flop works, right? Is we can store memory and we won't change the memory unless I click the clock first and then press my new input, in which case if the clock is pressed and I press the new input, then whatever that input is will then be stored in this Q and Q complement output. Okay, so there's only one more circuit that we need to talk about, and it's very similar to this SR flip-flop. The only difference is we only have one input. Okay, instead of S and R, we just have a data input. And so let's draw this circuit, and we'll talk about how this one works. So it's all the same. It looks almost completely the same. So we have those two NAND gates. We have the clock. So we have our clock there. All right, but these two inputs are going to be joined together, right, into a data input. So we only input one data, but this branch here actually has a NOT gate. So if I input data 1, so if my data is set to 1, then that means the input over here is 1 and the input here is on the other side of this NOT gate is going to be 0. Right, because NOT gate just takes whatever the input is and then takes the inverse of it. Okay, so that's how this part of it. The rest of the circuit is completely the same. So we have these two outputs going to the inputs of these two NAND gates. Then we do our flip-flop. So this output comes down to this input comes down to this output, right? And then we have our Q and Q complement. All right, where this is still S complement and this is still R complement. All right, and we can still write this as S and R, right here. Okay, so let's write this where we have D now. We have S, we have R. This is going to be a large truth table because there's lots of factors that we have to take into account. We have our clock, and we have our outputs, Q and the complement of Q. Okay, so if we set data to 1 and we set our clock to 1, okay, if our data is set to 1, like I was saying before, that means S is going to be whatever our data is, and then R is going to be the inverse of our data. So that's the same thing. So having a data set to 1 is the same thing as having an SR of 1, 0. Okay, and so if we set our clock to 1 and we look back at this chart now, we can see that if we had a clock of 1 and an S and R of 1 and 0, then we had an output of 1 and 0. All right, so now if we set our data to 0, S is going to be the same as whatever our data is. R is the inverse of that, so our R now is 1. Our clock, let's keep it set at 1. And so if we have, going back to this chart down here, right, if we have an S and R of 0 and 1 and we have a clock of 1, and then this output will be 0, 1. All right, so you can see that this is just just a slightly different version of what we had for this SR flip-flop here. And what it does is it takes whatever is stored in our data here and it stores it in the output Q. So if we have a 1 in data, we have a Q, we have a 1 in Q. If we have a 0 in data, we have a 0 in Q. All right, but it only gets stored if the clock is set to 1. So if we set, for instance, if we set our clock to 0, all right, it doesn't matter what any of these, doesn't matter what data is, and if data doesn't matter, then it doesn't matter what S and R are, because S and R are determined by whatever we set our data to. Right? It doesn't matter what those values are. Our output will be whatever our memory was. All right, so this is our truth table for the D-type flip-flop. Okay, where the only difference is that we have an input D that determines what S and R are, and then the rest is the same as what we determined over here. All right, so this is how we're able to store data, and this is how we're able to change based off the clock, how we're able to change what we have stored. All right, so what you'll see now is we'll build these three circuits. Basically, one is just this SR latch, so we'll be able to verify this truth table that we have here, and then we'll build this SR latch with the clock, so we'll have the full SR flip-flop, and then we'll be able to generate this truth table down here. And then finally, we'll add in this data portion, okay? And then we'll be able to generate this final data table there. All right, so we will see you once we get those circuits built. Okay, guys, so here we go. We got the first circuit built. So this will be for part A for this SR flip-flop lab. So this is just the intermediate SR flip-flop it's called, or it's also just called the SR latch, like I talked about in the introduction. So what we'll do is we'll go ahead and get the truth table. So in step 2 of part A, you can see that truth table. We'll go ahead and get that filled out for you, and then we'll go on to the next part. So you can see here, these are my 2 switches. The 2 NAND gates that I'm using are both located in this integrated chip, which is the 4011 chip. So the 4011 chip has 4 different NAND gates that we can utilize, but since we're only using 2, you can see that we're only using this left-hand side, which has the 2 NAND gates. This 2 switches are going to 2 of the inputs for the 2 different NAND gates, and we can see that the output for these are running to these 2 LEDs that we see at the top here, and then the top of these LEDs are then running all the way back to ground. Okay, so we're using these built-in LEDs on this particular circuit to be able to see our outputs. Okay, so right now we have the 0, 0 setting in. Remember that this is the invalid setting, so we're not going to really get, it just means that we have them both on. It's not really useful to us, so we're not really even going to talk about it that much. But let's go ahead and go through, if you follow along in the table that you see in step 2 there, let's go ahead and go through all of those inputs and see what we get as an output. Okay, so if we go S, so this is my S, my set, my reset. If I hit S1 and R0, you can see that we have a 0, 1 output. So this is my Q, and this is my Q, the complement to Q, or that Q bar, right? So the 1, 0, we get a 0, 1 output. Right now, if I click 1, 1, which is my memory output, you can see that this output doesn't change. It's still 0, 1. So if we go from 1, 0, so we go from 1, 0, right, to 1, 1, we still have the same output. Now, if we go to the reset state, which is 0, 1, so I lift up this finger, we go to 0, 1, you can see that our output does change. Okay, we now have, for 0, 1, we now have an output of 1, 0. All right, and if I go back to 1, 1, so I hit both of them again, you can see that that output doesn't change again. So 1, 1 in this case has a 1, 0 output because the previous state was the reset state. Okay, and then if I go back to 0, 0, you can see that they both light up. Okay, but again, we're not too worried about that last state. So that should help you fill out that truth table. So just to see it again, in case you missed it, right, we go from 1, 0, which has a 0, 1 output, to 1, 1, which doesn't change the output, right, because that's our memory state. Then we go from 0, 1, which is our reset, which does change, back to 1, 1, which doesn't change that one. So it's still at the 1, 0, and then we go to invalid state, which is the 0, 0. Okay, so that should help you fill out that first truth table. So this is for just part A. So that's all we really need to do for part A in this lab is fill out that truth table to confirm that the SR latch is working as we talked about in the introduction and as we expected. Okay, so what we'll do now is we will add in the rest of the SR flip-flop. So we'll add in the clock, and then we'll be able to get the truth table for that circuit. So we will be right back. All right, so we've got the circuit for part B built here. You can see it's quite a complicated circuit, probably one of the more complicated circuits in the lab. Over here we have our 4011, which has all of our NAND gates in it, and then over here is the 4001, which has all of the NOR gates. So both of these integrated circuits this has 4 NAND gates, this has the 4 NOR gates. Okay. Then we have our output of our NAND gates running to our 2 LEDs, which we see here. All right, and then those are then running to ground. Running to ground via this wire here. All right, so this is a circuit. You can pause it and then check it to the circuit that you can see in part B, and make sure that you understand how it was constructed and why it was constructed in this way. But what we're going to do is go ahead and check these outputs based off of these inputs. So remember, this is now a clocked SR flip-flop. This clock is this center switch here. Okay, so unless I'm pressing this clock button, no input going to S and to R should change our output, right? So if I press this button, S1, you can see that the output doesn't change, and if I press S3, you can see the output doesn't change. Only if I'm pressing the output while pressing clock will anything happen. Okay, so this nothing happened there because we already have our output is already on 0, 1, right? If I want a 1, 0 output, I hit that button and then hit clock, and then you can see that it goes ahead and switches over. So we store this bit of data only whenever, or we store this bit of data here in our output only whenever I'm hitting clock. So just again, as a demonstration, if I want to store 0, 1, I'll hit the S3 and then hit my clock button, and then it'll switch over, okay? And now if I want to store 1, 0, if I hit that button, it's not going to store it unless I hit that and then hit clock, and then it'll switch over. All right, so this kind of demonstrates the functionality of this typical SR flip-flop circuit. So what we'll do next is use a D-type flip-flop integrated circuit. So the circuit is technically a bit more complicated than what you see here. But since we're using an integrated circuit that has a lot of these components already built into it, the circuit itself will look a bit simpler. Okay, so we'll come back after we get that D-type flip-flop, and then we'll show you how that functions. But from this, you should be able to see how the truth table that I showed you in the introduction is able to be formed. All right, so we'll be back with that last part C, and then that'll be it for this lab. Okay, so this is the D-type flip-flop constructed. We have our D-type flip-flop integrated circuit right here. And then if you want to see how you can compare this to the figure in your manual to see, so you can double check that and see that how this compares to that circuit. But this is the circuit that you see in part C there, using this 4013 integrated circuit, which again is the D-type flip-flop. We have our clock is set to be this second switch here. So if we hit that clock, we can see that this first LED will light up. So that lets us know that our clock is happening. This output here is our Q, and then this output here is our Q complement. Okay. We also have this switch down here. So this switch is our data switch. So right now it's set to the 0 setting. If I flip it up, our data will be set to 1. So this is the single bit of data that we're trying to store in this output Q. Okay, so let's go ahead and flip it back down to 0. You can see that changing the data does nothing, right? And that's because I haven't yet pressed clock, okay? So if I switch that data down to 0, and then I press the clock, you can see that nothing happens because 0 is already stored in the output Q there, okay? Now, if I switch our data to 1 now, again, nothing happens because I have yet to press clock. But if my data is set to 1, and then I now press the clock button, we can see that that 1 is now stored in the output Q, and then that Q complement is changed to be, again, the complement of Q, so the opposite. So that goes to 0, okay? But for these D-type flip-flops, right, whatever our D is set to, once we hit the clock, that data will be stored in the Q output. All right, so that's how this functions, okay? Yeah, there's not much more to say for this lab. So that will be that we've demonstrated how you're able to get those truth tables that I talked about into the introduction. We've talked about, or you've seen how we've built the circuits, and then you've seen how we would have demonstrated how those truth tables would have been generated, right? So you can now take those truth tables and the data that we've gained from here, and then you can write up your report, just kind of describing, again, a lot of these digital circuits are going to be more qualitative descriptions of just what's happening and confirming that these integrated circuits work as designed, or work as we talked about in the introduction. All right, so that'll be it for this lab. So we will see you next week.